All right, today we are going to go through, finish up coffee cup calorimetry, and then we're also going to be covering Hess's Law, which is also known as the flippy thing in this class. You will see why it's called the flippy thing as we're doing it, but the real concept here is Hess's Law, and I will give you a location to look that up. I will also give you what it is as we're going through it. So go ahead, go back to your in-class problems packet, and we are going to go back to this slide, if I can get it to come up, where we're looking at the calorimetry, coffee cup calorimetry, and I'll kind of review some things there, but the main thing is to look at what information is this ultimately going to give us, how are we going to use this, and those types of things. I need to find my notes so that I don't tell you something wonky. All right, so a couple of things to consider as we're looking at a calorimeter is remember that no system that we can develop or do in the lab is ever going to be 100% efficient. There's always going to be loss somewhere. So that's where this heat capacity C comes in, and that's where this heat lost equation is coming in. We have to account for our system losing heat, losing energy somewhere. So every setup, every calorimeter has a certain heat loss. The manufacturer is going to give you that number. So we don't have to calculate the C. We're going to use it to determine how much heat is lost in that system. And before we can get our final answer, we have to be able to do that. So let's look at a couple of calorimetry equations. So looking at this first one, yes, because at the final end result, Q is going to be not necessarily negative. It's going to reverse the sign because we got to consider what's the system, what's the surrounding. Go ahead and say what you were going to say. It's measuring heat change. So since we're looking at the thermometer, we're looking at the effect on the thermometer, not the effect on the reaction. And that's what we have to keep in mind. Yes, sir. Yeah, it's gonna reverse the sign. But you don't do that until you've done everything else in the calculation or you screw up your calculation. All right. So we're looking at this first one, and it's when we have 105 grams of sodium hydroxide is dissolved in 150 grams of water, initially at 23.5 degrees Celsius in a coffee cup calorimeter. The final temperature is found to be 25.32. Calculate the heat liberated when sodium hydroxide dissolves in water. Assume the specific heat of the solution is the same as water. And no heat is absorbed by the calorimeter. So you see this statement right here? We're assuming we have a 100% efficient calorimeter, that we did not lose any heat to the surroundings, that nothing was lost. So we don't have to worry about that Q lost equation in this one. We are only going to use Q equals MC delta T. And the other thing is to assume that the solution is the same as water. What is the specific heat of water? 4.18 joules per gram degree Celsius. All right, so from here, it's just a matter of plugging things in. And then we're going to do one thing at the end. All right, so setting this up, what do I need? What am I going to start off with? All right, so So if we're looking at Q equals MC squared, what is, not MC squared, wow. Q equals MC delta T. What, no, it's not. So let's get back to this. So what, when we're talking about mass here, the M, what do you notice about the masses in this equation? You have two. So what do you think we have to do with it? It is a total mass. So we are going to add them. So it's going to be 1.095 grams plus. In this type of reaction, we should be looking at a total mass. All right, because that's everything that's in the calorimeter. All right. Now, if you're specifically comparing the metal to the water, that's a different thing. In this one, we are looking at the singular reaction. All right, so we're going to put our mass, so that means we have 151 point, not yet. You don't do that until the end. So 0.95 grams. All right. Then our C is 4.18 joules per gram degree Celsius. And our delta T, we're going to go, we end up at 25.32 minus 23.5, and then you just solve. So someone with a calculator, what is Q? All right, so when we solve this, we get 1,149 joules. I went to 4 sig figs because as we look through the equation, every piece of information that we have is 4 sig figs. All right, now, at this point, yesterday we made the statement that the heat of the reaction in calorimetry, the heat of reaction is equal to negative Q. So basically we change the sign of whatever we get. So what is our heat of reaction in this equation? We end up with negative 1149 joules. All right. So again, the reason why we do this is, yes, this is giving us the energy that is involved in this system, but we're wanting to know the energy that's happening in this reaction, so we need to know which direction it's going. So this is going to be on the product side, is all that's basically telling us. And that's where that is. So as you're answering these, when you're gonna change Q, make sure that you make this statement before you change the sign. Don't just change the sign without explaining why you did it. And this is ample explanation of why you changed the sign. It's just that when we're looking for heat of reaction, that is equal to negative Q. So looking at this problem is going to have a heat capacity. So we have that capital C, so that means we're going to have a Q loss that we have to deal with as well. So in this problem, we're going to have to deal with those at multiple places. So let's go ahead, set this one up. We have a 50-gram sample of 0.2 molar sodium bromide. When you come back, I don't really need it, but so we have a 50-gram sample of 0.2 molar sodium bromide at 23.65 degrees Celsius added to a coffee cup calorimeter containing 50 grams of 0.2 molar, what is that, silver nitrate at 23.65. If the heat capacity of the calorimeter is 65.0 joules per degree Celsius and the specific heat of the solution is 4.20 joules per gram degree Celsius, and the final temperature of the solution is 25.4 degrees Celsius. Calculate the heat released. So we're going to have to do a couple of things here. First off, we're going to have to do the let me check something. So let's just start on the left side with the thermo calculation. So looking through our setup here, we have 250-gram samples. So our final solution is going to have what mass? 100 grams. So we have 100 grams of solution, and our specific heat is 4.20 joules per gram degree Celsius. And then our delta T, so we only have two temperatures here. Our final temperature is 25.4 minus, what was our original, 23.65. All right, now from this step you should be able to solve for Q over here. Let's set up this other one. So Q lost is equal to, our capital C is 65 joules per degree Celsius times delta T, which again is the same delta T, so we have 25.4 minus 23.65 degrees Celsius. And what you need to recognize is that degrees Celsius is going to cancel in this one, leaving you with joules, and then grams, degrees Celsius, degrees Celsius. And so you end up with two statements in joules. So go ahead, solve for Q and Q lost on this. So what do we end up with? Anyone? 743. Let me check my calculations. I got 735. I ended up with 735. I'm wondering if you maybe put in a temperature wrong or something. All right. So we get 735 joules on the left. What do we get for our energy lost? Our heat lost? 114 joules. So the total Q is 735 joules plus 114 joules. So Q total equals 849 joules. Now, is this our final answer? No, because we need to make that statement. Heat of reaction equals negative Q. So delta H Rxn equals negative 849 joules. And that is your final answer. So does that make more sense as to what this whole Q lost is? It only applies in the calculation when they make this statement that the calorimeter has a heat capacity. So you're looking for this word, heat capacity, you're looking for this number. That should immediately cue you into that you're going to use this in the equation, and then you're going to end up saying Q total equals Q plus Q lost. All right. So when you see heat capacity, that lets you know that you're trying to get rid of that. All right. So there should be a Chem 1 textbook on your desk. I want you to go ahead, open up to page 862, I believe 862, 863 in that textbook. I'm just wanting to point out a table to you and showing you where I'm kind of getting some numbers from and all of that. The table that you're looking at, that you'll be looking at, is what's called the enthalpy for a heat of formation. And so if you look at the third column on there where it has this little symbol above it, the delta H with the little knot symbol and an F down there, what this knot symbol means is standard conditions. And the F is just telling us that that is formation. You're going to see different little symbols down there where the F is. Sometimes you'll see COMB, that means combustion. If you see RXN, that's reaction. It's just telling you where the energy is from. So the change in enthalpy, delta H, that accompanies the formation of 1 mole, that's going to be important, 1 mole of a compound from its elements with all the substances in their standard states. So a couple of things that you need to know about this is that a pure element has a heat of formation of 0. All right. Why would a pure element, or instead of saying a pure element, let's say a free element, or why would a pure element or a free element have a heat of formation of 0 joules? It's already as it is. It doesn't take any energy to form it. So what about oxygen? How would we write oxygen with a 0 heat of formation? How is oxygen found in nature? O2. So if you see O2, that's a 0 heat of formation. If you saw O, If you look on the table at just oxygen, what do 862? Yes, 2 and 3. Well, 2 specifically. So if you can just find, what is it, 01? I don't know if it'll say it on this one. Yes. All right. So if you notice, O2 is 0, but O3 ozone has a state. O1 would have a state too. This table just doesn't have it on there. So heat of formation for ozone, O3, is plus 142.7. All right. So we need to recognize, so O2's heat of formation equals 0, whereas O3 heat of formation equals 147. All right. I'm just wanting you to see this table so that you know where these numbers are coming from and know that they match up when we start manipulating these. So the only real skill that you need to know right now is how do we write a heat of formation equation, or how do we write a formation equation? So let's just say that we wanted to form glucose. Glucose is C6H12O6. So if I wanted to make glucose, what are the components that I need? Carbon plus hydrogen plus oxygen, and we're going to write oxygen as O2. And we do need H2 as well because hydrogen is diatomic. So now all we have to do is balance it. So it's going to take 6 carbons, 3 hydrogens, and then oxygen. It'll take 6 hydrogens, thank you, and 3 oxygens. So let me erase that and make that more clear. So yes, we need 6 hydrogens because we need 12 of that. All right, so that's heat of formation for that. Well, what if I did, coming back to this statement that we're looking at the formation of 1 mole. So what if we were looking at water? H2O. We only want to make 1 mole of water. So what is it going to take to do that? We have H2 plus O2 is how we find both of those in nature, but we can't do that under normal situations. So in heat of formation, you can have fractional coefficients. All right. So this is something that'll catch people and kind of freak people out with this. And we've seen it before when we were doing half reactions and all of that. You can have a fractional coefficient. So how do I get the 1 oxygen from this thing? So I would say 1/2. All right, and now I have a balanced formation of water, 1 mole of water. So we just have to kind of remember that and see that as we're going through it. So let's look at some information that you would have for heat of formation. All right, so this little table here, this little piece of information here would be an example. This would be an example set up for heat of formation of various elements or various compounds. So like we have the heat of formation of water, which is what we just saw, H2 plus 1/2 O2 yields H2O, and it's giving us a number that we have negative 285.6 kilojoules per mole H2O. For this other one, it's the formation of hydrogen chloride. I'm not sure if this is hydrogen chloride or hydrochloric acid because I don't have the state of matter if it's in, if it's a solid or a gas or a liquid. That makes a difference in this, but it takes 1/2 H2 plus 1/2 Cl gives us HCl, and that has a heat of formation of negative 92.3. And if we look this up on the table, we should find that these numbers should match what those numbers are on the table for each of those compounds. And then this last one, magnesium plus carbon, is 3/2 O2 to form magnesium carbonate, and that has a heat of formation of negative 1096 kilojoules per mole of it. All right, so ultimately, can y'all read this statement here? This is not in your notes. If I need to blow it up some, I can. All right, so we're going to start looking at what I put in the notes the other day as the flippy thing. This directly relates to Hess's law. Hess's law states that regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all the changes. So when we have a heat of formation table like this, and we're going to have maybe several steps along the way to form a certain compound or decompose a certain compound, we may have to change the direction of this reaction. And when we change that direction, that's going to cause us to change the sign as well. That's where we get the flip in this. So this law is a manifestation that enthalpy is a state function. It happens this way all the time. We just talked about enthalpy of formation. Another one that we want to look at is enthalpy of combustion. All right. So for enthalpy of combustion, we have a reaction that is a combustion reaction. And it's combustion of 1 mole of a substance. All right. So when we're talking about enthalpy of combustion, we're looking at a reaction where we combust 1 mole of a substance. So let's write a combustion reaction for ethanol. Can anyone tell me, or does anyone remember what the formula for ethanol is? Or at least how many carbons? 2. So we have 2 carbons, 5 hydrogens, and since it's ethanol, this means that we have a hydroxide attached to the end. All right, if we are combusting something, what am I going to add to it? In combustion, oxygen, O2. So we combine ethanol plus oxygen. The products are carbon dioxide and water. All right, so just so that we are clear and that we know, in a combustion reaction like this, when we're talking about enthalpy of combustion, since we're dealing with 1 mole, always, it is possible to have fractional coefficients in this as well, but I don't think this one ends up that way. So we get 2 carbons here, so I need 2 carbons there. I have 6 hydrogens, so I need 3 hydrogens here. And when I do that, I have 3 plus 4 oxygens, so 7 oxygens total. I have 1 oxygen here by itself, so I need 3 more there to get my 6 plus 1. All right. So this is combustion reaction for ethanol. Go ahead just to give yourself some practice because you'll be doing this in problems. I want a combustion reaction for propane. Propane is C3H8. And all I'm really asking you to do is just write the equation and balance it. All right. So now we are ready to do the flippy thing. So again, in this process for what we're calling the flippy thing, this is really just an application of Hess's law. And so basically what it is it's a manipulation of the heat of formations to get to a goal equation. Our goal equation in this is the one that we're given in the problem. So this is our goal equation. What lets me know that I'm going to apply Hess's law here is the fact that I'm given this table that gives me heat of formations for a multi-step process. So I'm trying to get to a goal of CO2, and I have to use 2 different formation equations to get there. So we're going to possibly end up flipping something. Now, as I'm looking through this one, I noticed a flaw with this first equation. What's wrong with our product here versus there's 2 oxygens, so we have to balance this one, and that's just a check real quick that it takes 1/2 O2 there. I don't know if it didn't transfer in the copy or if it was just expected for us to balance that, so we need to check for that. Now, so where do you start in this equation? The way that I do these, the way that I like to look at this, is I'm just going to take this first one and I'm going to look at it. What is the sole piece of information that I need from this equation that matches up with my goal equation? Carbon monoxide. So this is the piece of information that I need. What side is carbon monoxide on in our goal? Reactant side. So that means that I am going to flip this equation. I need CO over here. So when I do that, CO equals carbon plus O2, and it's 1/2 O2. What does that do to my heat of formation now? It flips it, or essentially it changes the sign. That's correct. So we, instead of having a negative 111 kilojoules, we have a positive 111. Go ahead and get in the habit of putting the sign for positive and negative on this, because remember, that's just telling us direction. All right. Now, I need to look at this second equation. What do I need out of this second equation? CO2. And so this one's going to stay in the same direction. So I have C plus O2 reacts to form CO2. All right. And on this one, my delta H remains the same, so I have a negative 394 kilojoules. So at this point, we want to combine our two formations to see if they match up with our goal. And one of so the first thing that we can do is we can cancel out anything that's alike from each one. So like I have a carbon here and a carbon here, so I'm going to cancel that. I have a half O2 here, and I have an O2 here. So if I cancel this one, what does that do to this one? Makes this a half. So if I get rid of a half of O2, then I have a half O2 here. So now, is there anything else that I can cancel on this? No, everything else is like it is. So if I write out the equation as it is, carbon monoxide plus 1/2 O2 reacts to form CO2. Does this match this? Oh, sorry, that's because this isn't matched. This isn't. This should have a half there too. All right. The reason why I know that is because I can't. I would have too many O's. I would have to have CO3 there. Yes, so it matches. All right. So since it matches, all we have to do now is total up our numbers here. So a positive 111 plus negative 394 gives us our delta H for the reaction is what? All right, so we should get a negative 283 kilojoules for this reaction. All right. I don't know. All right. So let me so in order to get you a little more comfortable doing this, and in order to give you some practice doing this, look at number 15. And so what's different about the setup of number 15 from the last one? What don't we have in this question? There's more steps. So our formation table, we have more steps, but we don't have a goal equation. So since we don't have a goal equation, we have to write the goal equation. All right. So it's what we're trying to get to with these steps. So, all right. All right, now that we have our goal equation, we can start looking back at each one of the steps. What is the one piece of information that we need out of this first equation to get to our goal? So we get ethane there. So ethane's in the product side on this one. It's in the reactant side on our goal. So what do we have to do to this problem? We have to flip it. So I'm going to go C2H6. One of the things you want to try to do with this is line up your arrows so that they stay in line. It'll make life easier as you're doing it. So C2H6, and then we have carbon plus hydrogen. So that's 2 carbons and 3 hydrogens. All right. The other thing that we're going to look at, what is our Since we flip the direction of the equation, what does that do to our number here? It makes it a positive, so it's going to be now it's going to be positive 84.68 kilojoules. All right. Looking at the second step, what's the one piece of information that we need out of this one? CO2. And, well, I mean, we're getting oxygen there too. But the sole thing, the one thing that this one contributes that nothing else contributes is CO2. CO2 is in the product side on this one, so we're going to leave it just as it is. CO2. And that's telling me that I have carbon plus oxygen. I don't need to make any changes, but look at our goal equation. How many carbon dioxides do they have? 2. So that means that I need 2 carbon dioxides, so that means I need 2 oxygens and 2 carbons there. Now, since I did that, what is that going to do to my number? Negative 394 times 2. So our number here is negative 788. Because this one, in the original equation that it was given us, it was in the product. We needed it in the reactant side. So we flipped the direction of it, and that means we changed the energy. Changed the direction of the energy flow. And the real name for a flippy thing is Hess's Law. But flippy thing is just a little bit easier, I guess, to remember. All right. And then this last one, what is the sole contribution of this equation that nothing else has? Water. And notice water is in the product side, so we're going to keep it on the product side. So H2O, and then we have O2 plus H2, and we need 3 moles of water in this. So we have 3 halves O2 and 3 H2s. So what does that do to this number? 286 times 3, which is 858 kilojoules. Now, to finish this off, we just have to make sure let me separate that so we can see. Finishing this off, we just have to make sure that what we did matches our goal, so we can go through and cancel. I have 2 carbons here and 2 carbons there, so it cancels out. I don't think anything else cancels. Yes, we have 3H2 here and 3H2 there. Now, what's going to happen with this 2O2 and 3O2? Yes, it becomes 7 halves O2. So we're going to have C2H6 plus 7 halves O2 yields 2CO2 plus 3H2O. So looking at this equation, does it match our goal equation? Yes. All right. Now, all you have to do at this part is add up this column of numbers, and that will give you your heat of reaction. So what is our overall? right, but what direction is it going? Negative 1,005, and I got 1,561, but I could be off on my rounding. All right, any questions?